Figure 1 shows an incomplete Born-Haber cycle for the formation of cesium iodide. The diagram is not to scale. Table 1 gives some values for standard enthalpy changes. Complete Figure 1 by writing the formulas including state symbols of the appropriate species on each of the 2 blank lines. So if we go back up and look, we can see we've got the ionic compound on the bottom line, and we've got the gaseous ions on the right-hand side. We need to remember that our Born-Haber cycle is showing us the strength of the ionic bonds by showing the relationship between the elements turning into the gaseous ions and then the ionic solid. So if we start to think about what changes are already present on our cycle, we can see that they've already shown us down here gaseous ions to solid ionic lattice. And if we look at the values, that would be the lattice formation, so minus 585. This arrow on the right hand side shows the enthalpy of lattice formation of cesium iodide. On the left hand side we would have the lattice just the enthalpy of formation of cesium iodide. And the enthalpy of formation is the enthalpy change when 1 mole of the compound is formed from its constituent elements in their standard state. So cesium is a solid metal, and iodine, I2, exists, that's its standard state, as a solid. And because we only need 1 iodine atom, we would need half a mole of iodine molecules. So that's our first line filled in. If we look then at the next change we've got, we're turning cesium solid to cesium gas. That is the enthalpy of atomization of cesium. Then we are turning half an iodine molecule solid into an iodine atom gas. That is the enthalpy of atomization of iodine. And since we can see that that's the one in the next part of the question, we're going to have to calculate because it's not in the table. And it is making 1 mole of gaseous iodine atom, so it is just 1 time the enthalpy of atomization. Then we're going from cesium gas and iodine gas to something on the top line. Now this is a positive enthalpy change, so this needs to be something we need to put energy in. So this would be cesium being ionized. And when it's ionized, an electron is lost. Nothing is happening to the iodine. So this is the first ionization energy of cesium, 376. And then coming down the other side, it will be the first electron affinity of iodine. And that's minus 314. And that's a down arrow and it's a minus number. So that all feels like it's making sense. We can look at our cycle and see that all our down arrows are negative and all our up arrows are positive. The next part of the question says calculate the enthalpy of atomization of iodine. Now there are a number of ways that you can approach this calculation. You could use Hess's law directly and say that the arrow that we're trying to calculate starts here and ends here. The short route is just going up the arrow X. The long route would be to go around the cycle in a different direction from the start to the end, and then follow the arrows around. So I'll do this method first. By this method, X equals, I'm going to come down this first arrow, so it's going to become minus 79. I'm going down the second arrow, it is already pointing down, so I'm going to keep the number as minus 337. And then I'm going to go up the next arrow, and then up the next arrow. They'll become positive because I'm travelling up, and then I'm coming down that last arrow, and it's 376. And then I'm going to type all that in my calculator and see what I get. That comes to 107 kilojoules per mole. So the arrow X is 107. Now you may have learnt a different method. You may have learnt the method that says formation is the sum of all the other arrows, assuming that the last one is lattice formation. If you've done that method, then our formation, minus 337 is equal to all our other arrows added up together. So 79 plus x plus 376 minus 314 minus 585. And if you type that into your calculator and rearrange, you will get the same answer. So either method works. You choose whichever one you are happy with. Next part of the question says the lattice enthalpy of formation of cesium iodide in table 1 is a value obtained by experiment. The value calculated using the perfect ionic model is minus 582. So in table 1, we can see that the value is minus 585. And the value from the perfect ionic model is minus 582. Those two numbers are almost identical. What that tells us is that cesium iodide is almost perfectly ionic. Use data from table 2 to show that this reaction is not feasible. That means that delta G would be greater than 0, because for a reaction to be feasible, delta G needs to be less than or equal to 0. So if it's not feasible, delta G is going to have to be greater than 0. So delta G, remember, is delta H minus T delta S. First thing we're going to need to do is work out delta S by doing the sum of the entropies of the products minus the sum of the entropies of the reactants. So we're going to add up the products, 82.8 for cesium, and then a half, 117. And then we're going to subtract the reactants, 130. We'll type that onto our calculator. And we've got 11.3. Now just remember that 11.3 is in joules per Kelvin per mole. When we're calculating delta G in kilojoules per mole, we're combining delta H already in kilojoules per mole. And we're going to minus, and it's giving us a temperature of 298 Kelvin. It's already in Kelvin, so that's okay. T times delta S. Now the delta S needs to be converted from joules into kilojoules. So I'm going to divide by 1,000 or times 10 to the minus 3. So if I do this calculation on my calculator, then I can see I'm getting a number of 334 kilojoules per mole. And since delta G is positive, that shows us that this reaction is not feasible. Okay, so we've shown by calculation it's not feasible.